Our next little notion here is, all right, what about e, as in y equals e to the x? We always had this e associated with natural log. Well, that's our next little piece of the puzzle. Now, this is the graph y is 1 over t. All right? Here's 1. And we know that the definition of natural log is the integral from 1 to x 1 over t dt. That's the definition of the natural log function. Now here's where e comes into play. It turns out e is a consequence of something we talked about much earlier in the semester, which seemed like about 5 years ago now. But before spring break, we talked about something called the intermediate value theorem. And it says this. This is the idea. All right. If I choose the function value of, let's say, 1.1, if I want to choose natural log of 1.1, now the specific number is not important. The question is, how would that computation be done? It would be from 1 to 1.1 of 1 over t dt. That would be just this small little sliver of surface area. And it should be very clear because this height is 1. This is the function 1 over t. So this height is 1. The length is 1. The width is much less than 1. Is it clear this area is less than 1? However, it can also be shown that if we go out far enough, and this is not too challenging to show, suppose I go out here to, let's say, 5. Now the question is, what is natural log of 5? Again, I'm picking 5 out of the blue sky. By the way, again, none of this, you do not need to be able to reproduce any of this. This is getting some understanding. So we'll get to some problems for you guys to actually work out soon enough. But for now, this is just understanding where things come from. So we have natural log of 1.1 is less than 1. But as you go further and further out, as we choose a larger and larger upper limit of integration, as this upper limit of integration starts at 1.1 and goes out to 5, this is getting larger and larger. Now what happens is we have this large blue area, a region to find that area. And it can be shown, it's not particularly challenging, that the integral from 1 to 5 of 1 over t dt, the specific number is not important, but what it can easily be shown is that value, this blue area, is greater than 1. So it starts out, actually it starts at, when x equals 1, it starts at 0. But as it goes, you get more and more and more area. This is less than 1. This is now greater than 1. This is less than 1. This is greater than 1. If this is less than 1 and this is greater than 1, what that means, of course, is somewhere there must be a value where the area is equal to 1. If it's less than 1 over here and it's greater than 1 over here, and if it's a continuous function, then there must be some value where it's equal to 1. The question is, what is that value? The answer to that question is e. This is the definition of the number e. The definition of the number e is this. It is the value E is the value whose natural log is equal to 1. That's the definition, and its existence is guaranteed by the intermediate value theorem. So, E, the definition of E is natural log of E is equal to 1. So the question is, why is the natural log of E equal to 1? Because that's the definition of the number. Now, it turns out that E is approximately equal to, it can be shown, 2.7182... blah, blah, blah. It turns out that's approximately that value, but that value was computed using some other approximation techniques. For our purposes, it suffices to say the natural log of e is equal to 1. The reason the natural log of e is equal to 1 is because that's the definition of e. Now, e is 2.718, and we recall from our basic knowledge from back in basic algebra, any value that's bigger than 0 and not equal 1, you're allowed to use that as the base for a logarithm, for an exponential function. You may, if you wish, write 2 to the x and work with that function. You may, if you wish, write 10 to the x, work with that function. You may, if you wish, write 14 to the x and use that function. Any value that's bigger than 0 and not 1 can be used. Well, it's bigger than 0 and not 1, we may use this as a function. And it turns out that is arguably one of the most important functions, arguably the most important function in all of basic mathematics. So we have the natural log function, which is defined from the fundamental theorem of calculus. We have e to the x, who can trace its origin back to the intermediate value theorem from calculus. So the upshot of all that is we now have these two functions in play, the natural log function and the exponential function. From your side of the camera, the question is, what do you need to be able to do? Well, you need to be able to do the derivatives and the antiderivatives of these two functions, and that's what we're going to be on about next.